All right, let's talk about requirements for data quality. So these are requirements for ANOVA. If you want to run ANOVA, all your observations must be independent from each other. The factors must be categorical or discrete. What to do if factors are not categorical, we will discuss in block number 3. The response is continuous. And then look, residuals must be normally distributed and population variances are equal. Why I call residuals here? Because it's almost impossible to investigate normality of your populations, because usually what is population? Population is a particular combination of factors, right? For example, in our previous example, population would be running a process, a reaction with temperature 120 and catalyst A. But you have only 2 values for this population. You have your sample size for this particular population consists of 2 values. So it's impossible to investigate normality in this case. But what you can do, you remember that we assume that the variance of all populations is the same. We simply remove average values, we remove all effects, and what is rest? Residuals. We can test for normality. It's a similar trick that we did for 2-sample t-test, if you remember. If you don't, I recommend you to watch this video again. And also the variances, we can check the variance of residuals instead of checking the variance of the real values again, right? So let me show you how to do it. But I also need to tell you that there is one more important requirement, is that factors are not confounded and they are balanced. What would be a confounded factors? Well, in this case, you can see also experiment where I have 2 parameters, temperature and pressure. And you can see that it looks like they are discrete. So we have only 2 values for temperature, 100 and 200 degrees, and also 2 values for the pressure, right? However, if you look at the table, you will find out that every time I have a low temperature, I have a low pressure. Every time I have a high temperature, I have a high pressure. So this situation we call it confounding. It means that your factors, they vary simultaneously, and therefore you will not be able to see if you have an effect. Is it effect from temperature or it's effect from the pressure? So you will not be able to resolve these effects because they are confounded. And you can calculate this confounding by just counting how many different combinations you have. So this is the table I have. You can see that we have 4 combinations where both pressure and temperature are low. We have 4 combinations where both pressure and temperature are high. And we have no combination here and no combination here. So this is a very clear confounding pattern. The ideal situation would be if you have 2 of each. So in this case, we would call this design unconfounded and balanced. And if you want to do that, you can use, for example, factorial design. You can Google for factorial design. But factorial design, it's simply where you have all possible combinations, at least full factorial design, all possible combinations of all your factors. And that's kind of one of the things that you can use when you plan your experiment, right? So make sure that you have no confoundings. That's also important. Now let's talk about the other assumptions. You remember that our assumptions are normality of residuals and equality of variance. Sometimes we call it homogeneity of variance, right? We remember that we already know how to check it, right? So we have a QQ plot to check normality visually. And then we have, for example, Shapiro-Wilk test or any other normality test to check it by using statistical testing. For the variation, you can use box plot, for example, for checking it visually. And then there is also a test for homogeneity of variance for this hypothesis that, for example, the variance of population A is the same as the variance of population B if you have a sample taken from these 2 populations, right? So you can also make a test for the homogeneity of variance. So let me show you how to do it. I will use R for the examples. Well, again, my examples will be based on this case that I used before. So I ran ANOVA to check the influence of 2 factors. It's the catalyst type and the temperature, and the response, it's the yield of this reaction, for example, in grams, right? So remember that I have found that both factors are significant, so it means that we need to check if we can trust these results. So this is the box plot, and then you can see that this is how residuals, it's residuals, you remember, it's for residuals. So the first box plot shows you how residuals depends on the levels of the catalyst type, and the second, how they depend on the temperature. And then you can see that the variation of these residuals, it's more or less the same. If you compare the boxes, you can see that they are almost identical, and it's true also here. So you can see the boxes are almost identical. So this is a good sign. So it means that very likely our default assumption is true. So the variance of population A, population B, and population C are the same for each, regardless which temperature you use. And also the variance for the temperature 120 and temperature 160 for these populations is the same. But it's a good idea to run a test in order to check it. And there are many tests that you can use for testing the homogeneity of variance. In R, there is one of the powerful tests that you have built in R, so you don't need to install anything. It's Fleener test, or it's actually Fleener killing test for homogeneity of variance. You simply provide the same formula, how residuals depends on G1, and then you can see that by default we assume they are equal, the variances are equal, and this is the p-value. So you can see that we cannot reject null hypothesis in this case. So we accept null hypothesis that the variance of these populations are equal. Right? And then you can do also this is for the second factor, for the temperature. And then you can see also the p-value is pretty high. So we accept this hypothesis as well. So from that point of view, it looks like we do not violate one of the assumption, one of the requirements for ANOVA, which is the equality or homogeneity of variance. Now we can also test the normality of residuals. You can see that this is the cuckoo plot for residuals I make in cuckoo line. And then actually you can see that they look okay, but you have a kind of maybe some groupings here, right? So let's run a test and then see how well test supports our null hypothesis that the residuals came from normally distributed population. And it means that also the values, the original values are also from normally distributed population, right? And then you can see it very well supported this null hypothesis. So we don't have any contradictions with null hypothesis. So it means that we can indeed trust the ANOVA results. I must say that ANOVA is pretty stable to minor violation from both normality and homogeneity of variance. So therefore, when you test for normality and when you test for homogeneity of variance, I recommend you to use the alpha, the significance level of 0.01. So if it's not below 0.01, then you can trust the ANOVA results. Okay. Now I'll show you an example what can go wrong. You remember that we made n-way ANOVA. So it means that we took two factors into account simultaneously. But what happens if we take only one factor into account, like if you make a t-test, right? So in this case, you remember ANOVA and t-test are the same if you have one factor with two levels. And this is what I did. You can see that I checked only effect of temperature. I didn't take into account the effect from the catalyst type. And now you can see a quite surprising result, right? So the p-value actually is quite large. So here the p-value is small. Here the p-value is large. Why so? Why it happened? Because we didn't take into account the variation of our values caused by having different catalyst type. All this variation, you can see this variation. Now you can find it in residuals. So before you can see the residual variation, this is sum of squared values. You remember sum of squared distances was 15.6. Now it's 883.3. Why? It's exactly 15.6 plus the variance from the catalyst type effect. Because here in this formula, we didn't take into account the catalyst type. By default, ANOVA accounts catalyst type as residuals, as random variation, and therefore it hides the real effect. So this is also very important takeaway message. If you run ANOVA, if you want to test some factors, test them all simultaneously. Run n-way ANOVA, don't run several one-way ANOVA. Actually, in this situation, because the systematic variation is so huge, you can actually see this. If you look at the residuals, you can clearly see very, very clear groupings, right? So one is from catalyst A, one is from catalyst B, one is from catalyst C. So in this case, you have no doubts that residuals show you some systematic pattern, because in this case, the effect is so big, you can clearly see it in the residuals. So that's another argument why you need to test to check residuals. But that's it. Now you are well equipped for testing effects of different factors to your outcome. So now you can use it on practice. Just remember that all these things will work if your sample is random and representative, if your factors are not confounded, and if you meet the requirements of normality and the homogeneity of variance. Okay. So that's the last video in block number 2. In block number 3, we will discuss what to do if your factors are numerical, if your factors are not categorical and not discrete.